All right. Happy Wednesday. So, on G, hopefully you all got that email and see that 2 people completed chapter 10's homework. There's a little button I'm supposed to click in order to populate it on our Canvas site. And if I forget that, then it locks it, and I can't undo that. So I'm sorry for that. It's just a bummer. So chapter 10 is not showing up under our modules. You have to go directly to the chief site to work that homework. Okay? I apologize for that. I did that a couple times last year. It just bums me out, but it just happens. If I don't do it right, it locks me out too. So, yes.
And the link to the Achieve site is in your homepage. So it's easy.
It is in the homepage. Thank you.
What does it do?
It's Sunday night. So you have time. Good? Okay, so, yes.
Will the test be over the material covered?
Yes, I'm going to go over what to expect for Friday. Okay. Let's finish up chapter 10. If you're following along, we're skimming over chapter 10. Okay, we're not delving into chapter 10. We're not doing titration calculations, which would be super fun. If you're taking a different chemistry with me, we go into titrations because they're very important, very cool, but we're not doing those. All right? We're having a basic understanding of pH. That's what we're working with, okay? Because I want us to understand that when we're talking about a pH of 7.4, when we're talking about a pH like in the liver of 2.8 or whatever, wherever the body fluid is that we're talking about, what does that actually mean? Ultimately means the amount of H plus that we're seeing there. Is there a lot of H plus? Not very much H plus, okay? So, this chapter also deals with neutralization reactions. We talked about that with sodium hydroxide and hydrochloric acid. There are a couple other ones that we can do. If I take something like sodium metal, sodium as a metal, and react it with hydrochloric acid, all right, it actually reacts pretty violently, and it forms sodium chloride and hydrogen gas. All right, so what happens, since electrons always go, hydrochloric acid basically looks like that. It has 8 electrons around it, Lewis dot structure coming out of chapter 6. I know that chlorine brings 7 to the party, hydrogen brings 1 to the party, so I have to have 8 electrons accounted for, so hydrochloric acid looks like that. I also know that hydrochloric acid is a strong acid. How do I know that?
Dissociate.
Say again?
Dissociate.
It dissociates 100%, but how do I know that?
It forms water and hydrogen molecules.
No, hold on. How do I know that?
Memorization.
I memorized it. Real basic, right? 6 strong acids, 8 strong bases, because I memorized them, all right? What it does, you're correct. That's what it does. Because it's strong, it dissociates 100%, falls apart. So, hydrochloric acid, when it sees sodium, it says, hey, I really, really, really would like your electrons. In fact, chlorine says to sodium, I want your electrons more than I want hydrogen's electrons. So it actually goes over and steals the electrons from sodium, forming sodium chloride. Now, one of the things we haven't talked about in here, and I won't talk about in here, is balancing chemical equations. You can see if you've had chemistry before, that equation is not balanced, right? So if we were in a general chemistry course, we would work through how is it that I have 2 hydrogens over here and only have 1 hydrogen here. I have to balance that, which means I need a 2 here, and we have to balance that somehow. We're not going to work with that. That's not the scope of this course, okay? We are setting a foundation on which I can explain to you the beauty and the miracle of carbon, and so balancing chemical equations is not one of those things, all right? But what you do need to know is metals and acids react, and they react to form salts, okay? Just like when we saw on Monday, if I have a strong base and a strong acid, it forms a salt and water. Okay, that one actually is balanced. So I don't have, that one's actually balanced, so I don't even have to worry about that one. All right? The other types, yes?
So when metals and acids react, does it always form a salt?
Yes,
Okay.
always. Yeah. So if you take any of the alkali metals or the alkali earth metals, and most of the transition metals, not all of them, they will react with acids to form salt. Okay? Good. A couple of them don't react. That's one of the reasons why these are like special. Even copper. These three here are really special. Gold and acid. It's pretty inert. Gold's pretty inert. One of the most inert molecules, or elements of the periodic table. It's also why it's one of the more cherished, because it's beautiful. The other way that I can do this is I can do a neutralization. So if I have stomach acid, strong acid in my stomach, and by the way, our stomach has hydrochloric acid in it, and it's pretty acidic. It's about 2 molar, and it has a really low pH. And we're talking 1 to 2, depending on what you have in your stomach. And that's why if you've ever had the privilege of throwing up, especially if it's like a triple barrel, both nasal passages and your mouth, you never forget it. And the reason why you never forget it is your linings of your throat and your mouth and your nose is not made to have that level of hydrochloric acid, and so we just all love that feeling of the chuck. And so it's also why if you throw up on like a car or something, that hydrochloric acid is caustic enough to actually eat the paint off of a car or something. It's just kind of really acidic stomach. And it's why it's really important for us to have that mucus lining to protect the actual tissue of the stomach. And if that gets out of balance, either from a bacteria or something, then we have ulcers and we have all these kinds of bad things that happen. But we can also just grab something off the shelf and neutralize it with something like bicarbonate. And if you just take a spoonful of bicarbonate, it actually neutralizes that stomach acid. Okay, so with this reaction, you can see that this is a mild base and this is a strong acid. So the base actually comes in and neutralizes it. And when it does so, and again, I'm not going to balance the chemical equation. If you want to after class, I would love to do that with you, but I don't want to make anybody uncomfortable because balancing chemical equations, again, is not the scope of this course. Okay? I spent enough time on GChem 1 and actually really enjoy it, but not for us. Okay? Yes?
So then acids and bases always react to form salt
Salts.
and water?
Yep. Not always water, but always salts. You can put that always there. Yeah. Because you look at the top one, it forms hydrogen gas, not water. Most reactions do form water as a byproduct. Okay, but not all. So that's a good clarification. Okay. Now, I mentioned briefly this whole idea of equilibrium. Okay, and the whole connected tank thing. Okay, we call this the Chartier's principle. If you have a system at equilibrium and you perturb it in one direction, it's going to shift. So if I add, it's going to shift. If I add, it's going to shift. If I take away, it's going to shift. It's always going to find some level of equilibrium. So here's the final piece of the chapter, buffer systems. Now, this is, I'm just going to tell you right now, working with buffered systems is very complex. So since we're doing like the 50,000 foot flyover of these chapters, you don't have to go down into the actual calculation of buffered systems. Buffered systems is actually a very complex, advanced topic in chemistry. And typically we have that second semester of GChem, and then we hit it again in our 4,000 level biochemistry with Dr. Chase. So it is really not one of those things that's just real trivial. But what we're going to do is just have the basic understandings of how they work, okay? Because here's the thing. If I have water, which has a pH of 7, and I add a tiny bit, we're talking a couple drops. If I had a beaker, say 400 or 500 milliliters of water, and I added a couple drops of hydrochloric acid into that, the pH is going to go massively to low. Okay, so this is going to go from a pH of 7 with a couple drops of HCl to a pH of approximately 1. It's going to go way, way down. Doesn't take much acid to cause the pH of that water to go way down. If I have water and I add sodium hydroxide to it, again, let's say I add sodium hydroxide to we're talking just a couple drops of sodium hydroxide. Sodium hydroxide is a solid, but if I had a solution, I add a couple drops to a water solution, it's going to go massively to sodium plus. Again, I'm not going to worry about balancing this, but it's going to take that pH and massively increase it. Okay, so this is going to be pH of around 13 to 14. Okay, so how does the body combat this? This is really important. How in a system can we combat this? Because within the blood, if we have a pH, and we'll see this when we get to the biochemistry component of this course, when we have pH of 7.4 for the blood, how is it that I can keep the pH of my blood from doing this massive swing if I have something acidic or something basic in my system? And the way that the body does this, and the way that we do this in a working laboratory, is through a buffer. Okay? So here's what a buffer is, and this is just memorization. A buffer is a weak acid and its conjugate base. That's memorization. A buffered system is a weak acid and its conjugate base. Okay? So how can I have a system where I can add acid and it not decrease its pH massively? How can I have a system where I add a base and it doesn't increase its pH massively? And so where you'll see this practically is in things like you'll talk about ketosis, acidosis. You'll talk about that in some of your classes, not necessarily the wildlife biology majors, but the nursing majors for sure. And the non-wildlife majors and the non-nursing majors, like Hannah, will never deal with this. But that's okay. You're going to have that knowledge that you're going to be able to take outside of this classroom. Okay, so how does this actually work? Well, let's say I take something like acetic acid. So if I take acetic acid, okay, and I have it in water, it is in a equilibrium system with its conjugate base. Okay, so its conjugate base looks like this. So again, this is in equilibrium. So buffer is a weak acid and its conjugate base. That is just memory. It is a weak, how do I know that acetic acid is a weak acid? Because I memorized the strong acids, and if it's not in that list, it's a weak acid. Okay, so it's pretty straightforward. All right, this isn't one of the 6, so it's a weak acid. So weak acid and its conjugate base. So this is the acid. So acid, base, conjugate acid, conjugate base, sorry, and conjugate acid. Okay? So here's what happens. And this is why this is such actually it's a really cool thing. Let's say I add acid to the system. Let's say I put in more H+. Okay? Somehow I add acid. Whether it's hydrochloric, whether it's hydrobromic, doesn't matter. If I add acid, notice I'm right now, before I add acid, I'm in equilibrium. My tanks or my pools are equal. If I add acid to the system, okay, I'm adding more acid. I'm adding more of that H right there. It might be from acetic, might be from something else. Might be from something I ate. Okay? What happens to the system? Well, the system actually is in this state of equilibrium, but it sees this negative, and the negative says, oh, I'll grab that and I'll switch this way to increase this. So it's a way that the system can actually have something added to it, but then modify itself. Before, when it was just water and I add the acid, it swings massively out of control. But because I have both base and acid in the system, if I add acid, the base grabs it. If I add base, the acid grabs it. And so it keeps the system at a lower swing of equilibrium. And this is exactly how the blood, the pH in our blood works. Oftentimes it's through the phosphate acid, or phosphoric acid and its conjugate base. So let's talk about a couple different systems that we might see. If I have hydrofluoric acid and potassium fluoride, this is a weak acid, this is its conjugate base. That is a buffered system. The conjugate base is the salt, if you will, of the acid. That's what you're going to be looking for. This is going to be very straightforward. On the exam on Friday, it's going to have several questions. I think there's 2 or 3 of them on buffers, because again, I want you to understand this. Which of these is a buffered system? So I might give you something like this. Is that a good buffered system? What's the definition of a buffer? Someone read it.
Weak acid and conjugate base.
Is that a weak acid in its conjugate base?
No.
That's a strong acid in its conjugate base. That's not a good buffered system. How do I know that's a strong acid? I memorized it. Okay? What about this one? Is that a good buffered system or a good buffering system? Someone? Anyone? Who wants to take a stab? Who wants to be daring? Yeah, it's a buffer. It's a great buffer. In fact, Dr. Chase uses this one all the time. It's great. So again, that's phosphoric acid. It's a weak acid because it's not one of the 6. That's its conjugate base, or the salt of the acid. Therefore, beautiful, beautiful buffered system. Okay? What about this one? Trying to make this a little bit. What about that one?
Yes.
Yes? Anybody? Anybody say no? Anybody say I don't know?
That's brutal.
What's an acid? Well, what's an acid?
That's brutal.
What's an acid?
Well, I was gonna say it's not a buffer,
It's not a buffer. Why is it not a buffer?
because HCO3 is a strong acid.
Okay, so hold on. Let's go back. Let's backtrack to Monday. What is an acid? Anybody?
Anything with that hydrogen ion.
Okay, any anion that has all of its hydrogens. Okay, so let's go back and let's review that. So the definition of an acid is all of those anions that we memorized. It doesn't matter if it's carbonate. It doesn't matter if it's phosphate. It doesn't matter if it's chlorate. It doesn't matter if it's nitrite or nitrate. It doesn't matter if it's chloride. It doesn't matter if it's even, I don't want to do nitrite, that's not fair. It doesn't matter if it's hydroxide, okay? Remember all of the anions that we worked through, both monatomic and diatomic, are these. We spent time reviewing these, working through these, and memorizing these, right? If I take and fully protonate those, those are acids. Carbonic acid, phosphoric acid, chloric acid, nitric acid, hydrochloric acid, dihydroxide acid, or water, okay? Which is, again, acid or base. That's the definition of an acid. What is the conjugate base of those acids? That doesn't count. See what's going on here? What is an acid? An acid is an anion that has all of its charge satisfied by hydrogens. All of its charge satisfied by hydrogens. All of its charge satisfied by hydrogen, all of its charge satisfied by hydrogen, all of its charge satisfied by hydrogen. So these are acids. Does that make sense? Because the Arrhenius definition of an acid is anything that produces an H+. That's what we talked about on Monday. The Bronsted-Lowry definition of an acid is also anything that produces an H+. So this is the presence of an acid. So H+, that is an acid. That is acid. That's all that an acid is, at least in the Bronsted-Lowry and the Arrhenius definition. Lewis is different, but those two are the same. Okay? Hydrogen, special little element. When you remove its electron, it becomes H+, becomes a proton. That is a proton. So therefore, any of the anions that I took, when I memorized the anions, and I satisfy them with full count of hydrogen, and even this one counts, it is by definition an acid. Now, certain combinations of these become strong acids. Those are the ones that dissociate completely. Of this list, which ones are they? HCl is one of them. Anyone else up here? So the only two I have up here that are strong from my list are nitric and hydrochloric. Therefore, those two cannot be buffer systems. So nitric acid and hydrochloric acid do not make good buffer systems, so we don't use them. It has to be a weak acid. Oh, carbonic. Oh, phosphoric. Oh, no, that's also strong. So I guess there's three that are strong. Chloric, nitric, and hydrochloric. So these two are the only ones up here that can make good buffered systems.
How do you determine the buffer?
It's weak acid and it's salt. And it doesn't matter what type of salt it is.
Okay.
Whether it's sodium, whether it's potassium, rubidium, cesium, lithium, beryllium, magnesium, titanium, chromium, it doesn't matter. We typically use the alkali metals and alkali earth metals, but it doesn't matter. It's just, it's literally the anion, its acid, and some form of its salt.
Okay, so the salt isn't important necessarily.
It just has to be its salt.
Okay.
What I'm looking for in a good conjugate, or in a good, is notice, phosphate and phosphate.
Yeah.
Right? So phosphate, and oh, that's its acid. Phosphate, oh, and that's its one form of it's salt or it's base. It's conjugate base.
Okay.
This one is phenomenal. Even down here where I had this, HF and KF. Notice, that's its acid, the fluoride, so hydrofluoric acid, potassium fluoride. Oh, that's a salt of its acid. Great, well, not really great one, that one's actually horrible, but it's a buffered system. Because again, it's a weak acid and it's conjugate base. We good? So, back to this one. They're both, oh, wait a minute, they're not the same. This is carbonate, this is bicarbonate. Those are different anions. Therefore, they're actually both bases. So that's not a buffered system. Okay? Let's try another one. What about that one? So let's go out on a limb, be brave, take a risk, gamble. I hear my three over here saying yes. Why?
That's going to be a weak acid.
That's a weak acid.
Yep. And that one, yeah. What is it? So conjugate base.
It's its conjugate base. Good. It's great. Yeah. Yeah. Acetic acid and calcium acetate. Sure. Yes.
How do you figure out the conjugate base? How do you figure out the?
Again, okay. Conjugate base. So remember, back. So let's go to hydrochloric acid. Let's just take our strong acid. Okay, so a very standard reaction. If I take hydrochloric acid and I add it to water, my pH slams low, 1 to 1, okay? This is my acid. And by the way, I'm going to ask you, how do I know that's the acid? Well, one, I memorized it, but it also is the hydrogen of my anion, right? That's what an acid is. It's an anion with its hydrogen. Okay? So that's an acid. The acid becomes the conjugate base. Okay? So the acid, yeah, so what happens in the real world, this comes over and grabs that. Electrons always go. So this is the acid, so water's behaving as the base in this example. So these electrons go grab that proton. So my base just grabbed the proton. So my base becomes the conjugate acid. Okay? So my acid then becomes the conjugate base. Yes?
So the simplest way I think to memorize this, especially what I picked up on, is you take the weak acid, which you know because you memorized the strong ones,
Uh-huh.
and then you just look at the conjugate base, and you'll see that they just match up with each other. And when they match up, that's a buffer.
You got it. That's all it is. It's no more complex than that. If you know your, this is why chapter 10 relies heavily on chapter 6. If you don't know these, you're not going to know these. Okay? So that whole list of anions, whether they're polyatomic or monoatomic, is predicated on or leads to our understanding of acids and bases. So here's the way to think of this. I'd love that to me is real helpful. Man, it's a workout today. Holy moly. Okay, so let's take a polyatomic anion. Let's do sulfate. Actually, let's do sulfite. I memorized that as sulfite. How do I know that that's sulfite? I memorized it. How do I know it's not sulfate? Well, one, I memorized it, but 8 has more oxygen, so sulfate is SO4, sulfite is SO3. So, everyone engage with me right now. How would I make this an acid? How many? Why 2? Because it needs to. So the acid of sulfite is going to be H2SO3, okay? And we're going to call that sulfurous acid, not sulfuric, but sulfurous. Are we all tracking with that? That's not very difficult. I do have to know what sulfite is. I do have to memorize that. But once I know that it's 2 minus, I know the acid of that has to have protons to satisfy those charges. Someone give me a conjugate base of sulfite. I don't care which one. Give me a conjugate base of sulfite.
NaSO.
Okay, someone besides my peanut gallery over here. You guys, I love that. Someone out here. Yes. Boom. K2SO3. K2SO3. Someone else give me one. Na2SO3. Someone give me another one. What was it? Li, sure, I'll take Li2. Li, not a very good one, but I'll take it. Whoop. Li2. Good, excellent. Someone give me another one. Yes?
Why is it not a good?
Yeah, lithium. So lithium is so small, and it's an anomaly. That's why lithium-ion batteries are the best batteries that we have because of the way it likes its electrons. So it doesn't make a good buffer, but I'm going to take that because again, for us, it doesn't matter, right? Just for the record, lithium-ion batteries, it's about 30 to 40-year-old technology, and that's as good as we've got. So we're not going to master solar or wind until we get better battery technology. So that's just one of those little like, that's the Achilles heel of this whole idea. We're got a long ways to go to be able to get there. We're not going to be able to fly a plane with batteries yet. Okay, so someone else give me another conjugate base.
RB2SO3.
Sure, I'll take RB. That would be a great one, yeah. Expensive, but I'll take that one. Rubidium's super expensive. Another one. Yes?
CA2SO3.
Good, good. Just Ca though, just CaSO3. Because remember, calcium is 2 plus. We could keep going. We could take every student in the class, all 53 of you, and we could add all of these to that list. What was the important thing? You got it. The conjugate base is the salt of the anion. The acid is only the hydrogens of the anion. So the acid conjugate base, if it's a weak acid and it's conjugate base, that is a buffered system. Okay? And the whole thing is, I've got acid and base at equilibrium. And I've got a lot of it. So if I had a couple drops of acid, I crank this up, it just goes over a little bit. If I'm at equilibrium, I add a couple drops of base, it goes whoop, and it buffers it. Because the base that's in there grabs the acid, or the acid that's in there grabs the base and neutralizes it. That is a buffered system. Yes?
Can you repeat what the conjugate
Conjugate
base is? Like what you said?
base is the salt of the anion. And that's for all of them, even the strong ones. Even the strong ones like hydrochloric acid, its conjugate base is the salt of the acid. But this is not a good buffering system because it's a strong acid. And strong acids do not buffer. They actually, again, that gets into some chemistry that we're just not going to get into as to why. Okay? We good? So here's the cool thing. you're seeing how it is that all of these chapters, the 3 that I picked out of the general chemistry section, chapter 4, chapter 6, and chapter 10 are all interrelated. You have to know what elements and atoms are to be able to build molecules. You have to be able to understand what molecules are to get to acids and bases. And here's the thing, on Monday, now we're going to have a little detour on Monday because this is a general ed course, so we're going to do a little detour on the scientific method on Monday. We're going to take an in-class quiz that you're all going to get 3 out of 3. And so I can check that box. That's Monday. Then we're going to get into organic chemistry, okay? So with these 3 chapters, it sets a foundation because when we get into organic chemistry and we start talking about aldehydes and ketones and carboxylic acids and esters and amides and nitriles and all these beautiful things, all these beautiful combinations of carbon, nitrogen, and oxygen, we have to have the foundation on why that makes sense, because carbon is a 4-bonded entity. It forms a tetrahedron. And not only does it form a tetrahedron, as Dr. Nagals, I think, in lab talked about, it forms a chiral tetrahedron, a left-handed and a right-handed. We have to understand that. It's called homochirality. It's one of the biggest mysteries in all of chemistry, by the way. One of the coolest things of all of chemistry, by the way. Can't wait to teach organic chemistry to you. So we've kind of slogged through general chemistry. I realize this isn't the most exciting stuff in the world, but wait till you get to carbon. Okay? When we get to carbon, it's like the switch is going to be flipped, and yours is going to be like, oh, I love carbon. Probably not, but you're going to see my love for carbon. All right? Okay, so what was chapter 4 on? Well, let's go back through and think about what we did. I purposely took you through chapter 4 to build the periodic table. The periodic table was a way of counting from 1 to 118, both in its protons and its electrons, right? And will there be questions on the exam as to what element has 23 protons? Yeah, there will be questions like that. And it's going to be real easy, because you'll look over here and go, 23, oh, it's right there. It's vanadium. If you can't count, we have other problems. So come see me after class. You can't count, all right? When I asked you to raise your hand, if you count to 1 to 118, everyone raised their hand. So, or at least everyone that was engaged. It was the same day that I told you to put your laptops away, and that wasn't a very fun day. But look at all these eyes. This is so great. Can't tell me how frustrating this is. It's not my thing. Okay, so 1 to 118. It also tells me how many electrons I have, from 1 to 118. So then we went into how is it then that these noble gases are special. Well, we talked about the electron configuration of these, and how it is that this fills the n equals 1, this fills the n equals 2, this fills the n equals 3, right? That's what these are over here, okay? So that's special. So if I'm a non-metal, I want to gain electrons to be special, taking the noble gases and sticking it right here. If I'm a metal, I want to lose electrons to look special. We talked about that. We built on that. Then we went through this exercise of the polyatomic anions, which were, again, memory work. Hydroxide, nitrate, nitrite, carbonate, acetate, cyanide, bicarbonate. Then we went phosphate, phosphide, hydrogen phosphate, dihydrogen phosphide, phosphate, sulfate, right? Sulfide, hydrogen phosphate. We went through that exercise. Perchloride, chloride, chloride, hypochlorite, right? We memorized the polyatomic anions, then we put together those with metals, and by the way, that became our, what we're calling up here, our conjugate bases, our salts, okay, our ionic compounds. We moved from that into one of the most important fundamental concepts in this entire semester, and that is, when in doubt, guess, starts with an E, electronegativity, okay? Electronegativity, we all memorized. Starting with fluorine at 4.0, we went across at 0.5. So we were 4 all the way at 0.5. We jumped down to the B student at 3.0. We were down by 0.5, 0.4, 0.3, okay? We memorized hydrogen stands up there alone at 2.1. We were golden. We used that to then understand polarity of molecules. And we talked about VSEPR, valence shell electron pair repulsion theory, where we had 2 And if they're tugging equally, it's a nonpolar molecule, we call that linear. If there's 3, we call that, not tetrahedral, trigonal planar, yeah. And then if we had 4, I heard it, yeah, tetrahedral. Okay, that's as far as we took Vesper. Then we use that to see that are the bonds pulling equally on that central atom. If they're pulling equally, doesn't matter how strong they are, it's a nonpolar molecule. If they're not pulling equally, it becomes a polar molecule. Okay? That was chapter 6. Then we use that to understand protons coming off of these anions, forming acids, or the hydroxide, which is the base, okay, or the conjugate base in this case. Those are all conjugate bases, okay? So that's what we've covered over the last 3 weeks of class. Any questions on that before I tell you what will kind of be on the exam, what to expect? Can we clarify it? Can we go back over any of it? I would love to. If not, we'll just move right on into what to expect on Friday.
I have a very simple question.
Good.
I'm just curious. There's 3 blank squares on like that bottom there.
Yeah.
Why? What?
Yeah, look, they're not blank over here.
So why did it not?
Yeah, so here's what happens. So one thing that we don't talk about with the periodic table, this one's newer. I bought this one about 6 years ago. I brought that one over from the old science building. So you can see that in the time that I bought that one and this one, it's changed. And now there's a newer one. All of these have been named. Okay, they all have names now.
They were not named.
They were not named.
But
They were not known. So anything that is etched or open like this, the font is open, is man-made, synthetic. They don't exist in nature. So even technetium, there's reasons for that. Technetium, we've never found it. We've had to make it. Okay, so synthetic, all of these are synthetic, all of these are synthetic. All right? If it's in brackets, okay, all the way up to 83, they're not stable, they decompose. They go through beta decay, alpha decay, and they fall apart. Bismuth 83 is your first stable isotope. Bismuth is stable. And bismuth is what you have in Pepto-Bismol, the pink stuff. Okay, that's bismuth. All right? So the rest of them are unstable. If it's red, it's a gas at room temperature. If it's blue, it's a liquid at room temperature. So you can see gas up there, you can see mercury, and bromine are the only 2 liquids at room temperature. Okay, cool. So there's a lot more on this. And here's a little trivia.